This is theta. So the normal can be defined easily in these axes. Why? Because it's this is theta, so the normal is easily defined. The normal is negative sine theta and cosine theta. So the normal at each point is also a matrix like this. Okay? Negative sine thetas, cosine thetas. Okay, very good. So here, if we call bias of R, it takes a point. Here is our point, the first control point, and it take the vortex, so x, y bound of J, right? Because we're summing over J the number of bound vortices. This is the point, your point, this is the vortex. I'm done with the bias of R. Bias of R gives you what?
Induce.
Gives you what?
The U induced.
The U induced. Very good. So, but I don't need the total U induced. I need what? I need the normal component only. So I'm going to do the dot product. Either use the command dot or just dot it like this. NP of I and anything and sum over these, right? So this guy will just multiply component by component, the x's together, the y. The result of this bias of R is just two numbers, right? Two numbers. The induced velocity, the components of the induced velocity, this vortex on that point. Two numbers. This guy of I, one row of the normal, is also two numbers, sine theta and cosine theta. Multiply them together, component by component, to do the dot product and sum. So the result now here is V normal, right? The V normal due to all the bound vortices, but without the strength. So this is times, has to be multiplied by gamma J, gamma bound of J, but they are unknowns, right? Okay? Is it the total normal velocity at the first point, or we're missing more? Is it the total, or we're missing more? What did we get so far? What did we get?
We didn't include the trailing edge wake. Vortex.
We included the trailing edge, but we didn't include the wake. This is all bound vortices. Bound, x, y bound on the first control point. We need to do this exact same summation. So plus summation, maybe j or whatever, 1, but now the number of wake points. These are not known a priori, right? They are increased as simulation time go. The exact same thing. Everything will come down the same. Where should I change? Where should I change? Where should I change? Come on, guys. Where should I change?
Strength.
The strength, very good. And what else? And the location of the vortex, right? So this will be x, y, not bound, not controllable, it's x, y wake of J, and the same, exact same thing, and gamma wake of J. The only difference that gamma wake is known, right? So if this is point 1, I can make it for any point I. So this will be simply I, and that's it, right? Here is I, done. So we will call this AIJ. Okay? We'll call this AIJ. So at the end of the day, the V normal 1 up to V normal N is equal to A11 times gamma bound 1 up to A1n gamma bound n, but also A1n plus 1 times gamma bound n plus 1. The effect of all bound vortices on the control points. N plus 1 bound vortices on the wing, but in the control points. Okay? So this is AN1, ANN, and ANN plus 1. Okay? At each time step. So this is the bound plus the wake, right? But the wake is known, so I'll move it to the right hand side. So I'll say this is equal to the right hand side, where the right hand side J where this right hand side is what? Right hand side includes what? Right hand side includes what? What's the obvious thing in the right hand side? What's the obvious thing in the right hand side? What should be in the right hand side?
The point.
The V motion, this should be in the right hand side, right? At least this should be. So this guy's V motion, this should be given at this point I. Normal, right? And what else? What else? So we should not proceed unless you guys get it. I mean, it's pointless if I'm just writing myself. If you, let's start from the beginning. Where did you just shut off? Just let me know. Don't proceed. Don't let me go unless you get the thing. We're not doing rocket science. We're doing very simple stuff. We're saying, okay, we have n point vortices, and I need n equations. And the n equations are simply the V normal at each panel due to all these vortices should equal to the V normal due to motion. Okay? The issue is that when I get the V normal at each panel, it's due to all vortices. So it's due to your unknowns and also something in the way. So I have to account for all. We get the effect of a single vortex on a single point by this function, bias of R. Takes two coordinates and gives you two components for the U induced. So now if I want to get the V normal at point 1 or point I, it doesn't matter. It's from all summation, all vortices in the bound. We have bound run from J equal 1 to N plus 1. These are known from the beginning. It's your mesh. You're going to decide, I'm going to divide my wing into 40 panels. So N is known. N wake at the beginning is 0, but then it increases as time simulation goes. So at each time step, this is, okay, it's known, it's fixed. So I'm summing all over the bound vortices over the wing, all over the wake vortices in the wake. It's the exact same expression. Here I'm multiplying by gamma bound, which is unknown. Here I'm multiplying by gamma wake, which is known. So this whole term, is what? It's this term times gamma 1, plus this term times gamma 2, plus this term times gamma 3. Okay, so we have all things times all the gammas. So we can write it in a matrix form like this. Times all the gammas. So this is the first term only. The second term is very similar, but I'm multiplying not by gamma bound anymore, I'm multiplying by gamma wake. Gamma wake is known. So it's very convenient to move it to the right hand side. So now the right hand side has two parts. The V motion, V normal motion from the beginning, and the wake part that I moved. So the right hand side has the V motion minus the wake part because it's coming from the left hand side. Okay? So minus this exact expression. So minus whatever the word you want to call it. here it is. So minus summation J1 to number of wake. I'm just copying this guy, exactly the same, okay? So sum of values of R, it takes two things. Point, it's the point I, so x, y, control point I, and the vortex. So it's x, y, wake of J. The bias of R gives you two numbers. It's not the normal, so I need to multiply it by the normal, right? Of I and anything. The normal at the point I. Here is the sum. Then I will multiply by gamma wake of J. So the motion minus whatever coming from the left hand side of the wake, because these are known already. Any question about that? So this is our system of equations. A times gamma is equal right hand side. So here for I equal 1 to n, j equal 1 to n plus 1, here is the expression for aij, right? What about the last row? The last row is corresponding to the last equation. What is the n plus 1 equation? What's the n plus 1 equation? What we said you're going to use for it?
The conservation of circulation.
The conservation of circulation. So summation of all vortices equals 0. So gamma 1 plus gamma 2 plus gamma 3 plus gamma 4 plus yada yada, right? Equal 0. So gamma 1 means 1 times gamma 1, 1 times gamma 2, 1 times gamma n plus 1. These are the unknowns. This should be added to the wake equals 0. Because the wake is known, I'll move it to the right hand side as well. So this is what? What should be here? Can you suggest? This is easy. What should be here? What should be here? Is it 0? What should be here? Should I write 0 first? Let's set it down. Should I write 0 here? Okay, so what should I write? What does the left hand side represent now? Can you tell me what does this represent? What does this represent?
All the bound vortex.
All the bound vortices, okay. What does all bound vortices equal to?
V normal motion.
I'm sorry?
V normal motion.
No, this is not a V normal equation. We said that this equation, right? And you agree this equation, summation all gammas equals 0. You are saying that the left hand side is summation all the bound vortices over the airfoil. So what should be the left hand side now? Yeah, summation gamma wake in negative because it moved. So this is some negative gamma wake total, right? That's it. So this is our system that we're gonna solve at each time step to get the gammas. Okay? After we get the gammas, what do we do with them? We can get anything. In particular, we can get the loads. We can get the velocity at each point. How you get the velocity at each point? Can you tell me how can I get a velocity at this point, for example? I have the coordinates of my point that I want to get the velocity at. How can you get the velocity at this point? Any idea? How can we get the velocity at this point? You induce due to what?
Into the
Gamma wake, okay. Yeah, we know the gamma wake, we can do that. And sum all these. Is it the total or we need something more? So the V induced due to these guys, that's right. What else?
Gamma bound.
And gamma bound also, because we already solved it for the gamma bound. They are known now. So U induced due to this guy due to bound, right? And if you want to get it relative, so this is the absolute velocity or inertia. If you want to get it relative to the airfoil, you need to subtract the velocity of the airfoil, okay? So this is if I want to get the velocity at any point. What if I want to get the pressure on the airfoil? We already wrote this equation before for the unsteady Bernoulli equation, right? This form of it in terms of vortices, in terms of circulation. P at any x, delta pressure at any x is rho u gamma bound at that x, if you remember, plus rho partial t integral from the leading edge to x gamma bound of zeta dz. We wrote this equation before, which is right from the unsteady Bernoulli equation. Okay, let's apply it. So delta P at a panel I equals to what? Rho U times what? Can you get me this guy? What's this guy? This is the circulation, right? Distribution, circulation per unit length. We have gammas at each panel. So how you get the distribution? Well, let's assume that it's constant over the panel. So this is gamma bound of the panel divided by the spacing d, right? Per meter, because this guy is gamma per meter, it's distribution. Okay, so we're going to divide this guy by our unit width plus rho times. Look at this, this is summation. I'm at point x, okay? So this is summation of all bound vortices up to this point x, okay? So this is easy. This is sum of all gamma bound from the beginning up to this I, correct? Yeah, but we need to do partial t for this. Partial t numerically, the straightforward thing is do this time minus last time divided by delta t, right? So this guy is this time minus the exact same thing. So sum of gamma bound old. So we need to record the old version of it, okay?
I minus 1.
This is all divided by delta t. So we're done. So we got the pressure at any station. We can sum the pressure to get the lift. Any question? So let's start do it together. Or before, actually, we can do a flow chart just to know what we're doing. Any questions so far, please? If you have a question, just stop me. This too